All right. Hello, friends. MoNaCo here. Fourth video, about halfway through the video series for this unit. Um, we're talking about moles and stoichiometry for our unit, and we're going to begin balancing chemical equations at this point. Now, we need to show chemical equations that obey the law of conservation of mass to balance out that the atoms were there before and afterwards. So that's what today's lesson is about. But why would we do this? How does it have an effect on our equations? Well, any atoms that were before a reaction took place, and they have to be shown after the reaction is completed. Simply put, we chemists don't have the ability to make atoms disappear. They can just change forms, change shapes, be rearranged into new compounds, but they don't actually just pop into or out of existence. That's not allowed. That's called the law of conservation of mass. Anything that has mass, like protons, neutrons, electrons, everything, essentially, can't be created or destroyed. It can only be rearranged in chemical reactions. So a chemical equation is a set of symbols that state the products and reactants in a chemical reaction. The products are always on the right side, and the reactants are always on the left side. So reactants, starting substances, they're on the left of the arrow, and the products are the things that are produced or made in a reaction. They're always on the right hand of that arrow. For an example, the reactants are over here, and the products over here, and this is the reaction itself. The arrow itself is the reaction. And the way this is read, it says 2 moles of sodium and 2 moles of water react to create 2 moles of sodium hydroxide and 1 mole of hydrogen gas. We'll get there eventually. Chemical equations must be balanced. Think of that arrow as like an equal sign. The law of conservation of mass says that mass cannot be created or destroyed. It can only be rearranged. Now, balancing equations, it's like the number of moles of each element on the reactants, the left. So the number of moles of atoms on the left has to be equal to the number of moles of atoms on the right. That's really it. Before and after, everything has to match up. Coefficients and subscripts tell us how many we have of each element. What are coefficients and subscripts, you might ask? Well, coefficients are numbers that come out in front of the symbols, and subscripts are the ones that come after. Note how there's 1 mole of carbon and 2 moles of oxygen. 1 mole of carbon, 2 moles of oxygen. That's what it means to be balanced. The same amount of stuff is on either side of the arrow. So let's look through this problem. How does this unbalanced equation violate the law of conservation of mass? The answer is this equation, oxygen would have to be destroyed. There's only 1 less in the product side. If we count, we've got 1 oxygen over here, but we had 2 over here. So 1 of them went missing. That's not allowed. A coefficient is the integer in front of the element or compound. It's the number I put out in front, which indicates the number of moles present. The subscript is the integer to the lower right of the element, which indicates the number of atoms that are present. Okay, so in this case, we've got different coefficients and subscripts. Let's look here. What do we use to balance equations? We use coefficients. We never change the subscripts in a formula because that's changing the formula and the ratio of the atoms, and that's just not allowed. So in this example, let's look for coefficients and subscripts. So for coefficients, we're looking for numbers out front, and subscripts, we're looking for numbers on below. So coefficients, in the AG, it's a 2. For the S, it's a 1 because there's no number actually written there. For AG2S, since there's no number out front, we have to assume that it's a 1. Okay, I'll do my subscripts in a different color, I'm sorry. So subscripts, on AG, there's no number there, so we assume that it's a 1. For S, there's no number there, so we assume it's a 1. For AG2S, there's no subscript. Well, there's a subscript for the AG, that's a 2, and there's a subscript for the S, it's a 1. So again, subscripts and coefficients are things that we know subscripts well from previous units in grand formula mass, but the coefficients are what we're going to use to balance equations. So here's a method for balancing equations. It's a 5-step method, okay? And Mr. Milks and I both have our own ways of saying this, but it's a very cyclical problem-solving method that requires you to do, count, compare, coefficient, and repeat, a process over and over until both sides of your equation balance up. The only way to do this is to get some practice with it. I'm going to do a few examples for us here on the video, but most of the time we're going to be practicing this in class. I've got a few interactives that I want you to try out. So my method is count, coefficient, compare, repeat. So the first thing I do is I count the atoms of each type on each side of the equation. I like to keep them in order so that I don't get mixed up. So I look on the left side and I see that the H2 has a subscript of 2 and a coefficient of 1. So there's 2 total hydrogens on the left side of the reaction. I look at the oxygen and I see there's a subscript of 2 for the oxygen, a coefficient of 1. So they say there's 2 total oxygens for the reactants. Now on the product side of things, I look for hydrogen. I see there's a 2 subscript and a coefficient of 1. So 2 times 1, there's 2 hydrogens. For oxygen, there's a 1 subscript, and 1 times 1 means there's 1 total oxygen on the right side. So I've counted. Now I have to compare. Do I match to the same number of hydrogens on both sides of my reaction? Well, yeah, hydrogen matches. Does the oxygen match? No, it doesn't, which is where we get to the coefficient. I have to put a coefficient in on the line in front of one of these species up here to make something balance. And I can see that I need 2 oxygens on both sides. So if I put a 2 as a coefficient out there, I then have to count my atoms again. Now, in this case, I have 2 times 2 is 4 hydrogens, and 2 times 1 is 2 oxygens. Now I counted, I compare. My hydrogens don't match now, but my oxygens do. So now I got to go put a coefficient in on the left side, because again, count, coefficient, compare, repeat. Left side, what can I do to get 4 hydrogens? Well, they come in packages of 2. If I put a 2 out in here in front of my coefficient, 2 times 2 turns to 4. So now I have 4 hydrogens. I didn't change my oxygen, so now I got 4 hydrogens on the left, 4 hydrogens on the right, 2 oxygen on the left, 2 oxygen on the right. I am now a balanced equation. So I can put the coefficient of 1 in for O2 because that's what it was all along. So in this process, count, coefficient, compare, repeat, you are just going through a cyclic method of trying to get the number and type of atoms and elements on each side to match up. Na, H, and O. Na, H, and O. You have to be careful in this example because notice how hydrogen is coming from 2 different locations. So you have to take that into consideration when you're trying to solve this problem. I want you to try that one on your own. If you get it wrong, it's okay. I want to see that you've attempted to do that. We got a lot of practice to do in class, and you're not going to learn it all just from this little video here. Count, compare, coefficient, repeat. Let's count our atoms, carbons, oxygens, and hydrogens on the left. Carbons, oxygens, and hydrogens on the right. Keep in mind, beware, there's oxygen in 2 different locations here. So it's like the previous example, but the oxygen has been split up. It's been split up in a lot of different spots. So this is a problem that you just have to do the count, compare, coefficient, repeat over and over again. Again, I want to see for credit that you've tried to solve and balance this problem. When it all comes down, last notes is this. When balancing chemical equations, polyatomic ions, those elements from table E, must be balanced as a single element rather than separate. Because if you try to do them separate, it's going to make your job a lot harder. But if you keep them together in their shields, like this, see there? That way you can count it as a single element. So you only have to count the polyatomic ion as a chunk. Okay, we call it chunks, we call it shields, whatever you want to call it. Keep it as a chunk, because if you don't, it's going to make your job much, much harder in the long run. You'll take more steps, but you will eventually get to the same answer. So for an example, I'm just going to break one down here for you. So I'm going to count my elements. I've got Al, but I also see I've got SO4 on both sides of this equation. So I'm going to count that as an SO4, the whole thing together, because I saw that it didn't get rearranged or broken up as it went. I also have calcium, and this OH looks to be the same on both sides as well. So when I count, compare, coefficient, repeat here, I am actually making myself have a shortcut because I am counting my polyatomic ions as a chunk, and I'm keeping them together. If I didn't, I'd still get to the same answer. It would just take me a lot longer. So over here on the left side, I got 2 aluminums times 1, so that's 2. I got 3 SO4s, I got 1 calcium, and I have 2 hydroxides, OHs. On the right side, I have 1 aluminum, 3 hydroxide, 1 calcium, and 1 SO4. From this point, it's count, coefficient, compare, repeat, over and over. And again, keep your polyatomic ions as a chunk. I don't expect you to understand this down cold yet because it takes a lot of practice to get this. So there's a lot of practice pages, 11 through 14, plus a small mini multiple choice assignment on our castleLearning.com. So thanks for watching, and definitely be prepared to do a lot of practice of this in class because that's the only way you're going to get it. Thanks again. Bye now.